So our common gate amplifier should look something like this. We have some drain resistance RD. We're going to take our output voltage there. We have some source resistance RS. And at the source is where we apply our input signal. Here's CN, RN, here's our input signal, VN of T, and then over here on the right hand side of the circuit, we have our biasing network, which is our simple voltage divider. Here's RA. And here is RB. This voltage is obviously then VDD. Give you guys a minute to write this down, then we'll go through large signal and small signal just like we did last time. Let me know when I can scroll and draw this again. RA, yes. Let me make this better. RA, yes. All right, I'm getting bored, so I'm scrolling. So our large signal or DC model is going to look very similar. Here we have our power supply, VDD. Here's RD. Here's RN. This guy down here is RS. RA. And RB. So we can see pretty easily that the voltage applied at our gate terminal is VDD times RB over RA plus RB. Our voltage at our drain terminal, VD, is equal to VDD minus RD times ID, where this is our large signal drain current. And our source voltage, no, go away. VS is equal to ID times RS. So if we were to form a system using these three relationships, what we would find is that 1/2 mu n C ox W over L times RS times VGS squared plus 1 minus mu n C ox W over L VTH times RS times VGS plus 1/2 mu n C ox W over L VTH squared RS minus VDD RB over RA plus RB is equal to 0. And so just for the sake of argument, I'm going to group these guys together and call them A. I'm going to group these guys together and call them B. I'm going to group these guys together and call them C. And since it's a quadratic system, we could say that VGS is negative B plus the square root of B squared minus 4AC divided by 2A, where I'm throwing away my negative solution because if I include my negative solution, that one will never make the transistor turn on, so it doesn't do anything for us. And once I know VGS, ID is simply 1/2 UN Cox W over L VGS minus VTH squared. So our basic saturation current. Okay. So this is the results of, I think in 336, maybe it's 335. When we analyze the 4 resistor biasing network, this is literally exactly that. Okay. So on the DC side, nothing remotely approaching new for at least the majority of us. Can I move to small signal now? All right. So our small signal model is going to look something like this. So let's say that this guy is my gate. This is going to be RA in parallel with RB. Here's my small signal VGS between my source and ground. I have that resistance RS. I also have RN in series with VN. Here's GM VGS. Here's R out. And between my drain and my power supply, which just to remind you, my power supply is treated as an AC ground. I have that resistance RD. And the drain terminal is where I take my output voltage up. So this small signal model is a little complicated, all right? So a couple of things that we can do to potentially simplify some things here. First, is that parallel combination of RA and RB going to affect our small signal model in any way, shape, or form? No, right? So it's a set of resistors, it's open circuited, which means no current's going to flow through it, which means no voltage drop is going to occur over it. So RA and RB effectively do not exist in the small signal model at all, or at least they don't contribute to anything. Since that means that my gate terminal is effectively ground, I could say that this voltage right here is VGS as well. And that's going to help me a little bit. So I'm going to wind up applying Kirchhoff's current law at a couple of places to develop a relationship for my voltage gain here. And so while I am doing that, I'm going to go ahead and express some of these currents. So the current flowing through resistor RS should be negative VGS divided by RS. The current flowing through my resistor Rn is going to wind up being negative VGS minus Vn divided by Rn. Current flowing through my resistor R out is going to be V out plus VGS divided by R out. And the current flowing down through my resistor RD is just V out divided by RD. So before we start rocking and rolling with this, anybody got any questions about how we got any of these currents? I'm just effectively going to apply nodal analysis to this problem. And so I need to figure out how I can express all of my currents flowing through my resistors. So it's always the node where the current started at minus the node where the current lines up divided by the resistor value. And unfortunately, we wind up with a bunch of negative signs in weird places based on the polarity of that voltage VGS. So if we apply KCL at our output node or our drain node, because they're the same thing, what we'll wind up getting is V out divided by RD plus V out plus VGS divided by R out. I hope it's okay with you guys. I'm dropping the as a function of time dependencies here because it's just going to get annoying and in the way. And then I'll also have plus GM VGS is equal to 0. And I can algebraically manipulate this guy a little bit, and we'll find that we have V out over RD plus V out over R out is equal to negative VGS divided by R out plus GM VGS. And with a little bit more algebra, I can then say that V out multiplied by 1 over RD plus 1 over R out is equal to negative VGS multiplied by GM plus 1 over R out. And from this, I can say that VGS, or actually let's leave it as negative VGS because that's going to pop up a lot, is going to be equal to V out times 1 over RD plus 1 over R out divided by GM plus 1 over R out, or V out multiplied by 1 plus R out over RD divided by 1 plus GM R out. So I've established I don't want to call it simple relationship between V out and VGS, but a relationship that we're going to wind up doing a whole heck of a lot of substitution with. So now applying ACL at our source node. Out and our dependent current source all contributing. So that's going to look like negative VGS over RS plus negative VGS minus VN over RN minus GM VGS minus Vout plus VGS over Rout is equal to 0. And that's going to be negative VGS over RS minus VGS over RN minus GM VGS minus VGS over Rout minus Vout over Rout is equal to VN over RN, factoring out my common term of negative VGS. I'm going to have 1 over RS plus 1 over RN plus GM plus 1 over Rout minus Vout over Rout is equal to VN over RN. And now for a substitution, since I know what VGS is in terms of Vout, which is what we solved for up there, I wind up getting Vout multiplied by a factor of 1 plus Rout over RD divided by 1 plus GM Rout times 1 over RS plus 1 over RN plus GM plus 1 over Rout minus 1 over Rout is equal to VN over RN. And from here, my voltage gain, Vout divided by VN, is RN multiplied by 1, plus Rout over RD divided by 1 plus GM Rout 1 over RS plus 1 over RN plus GM plus 1 over Rout. Goodness. Close this guy. Minus 1 over Rout. Close this guy. And hold on just a second here. I don't have this in my notes, but I'm trying. But I know that it's a mistake. I'm trying to figure out how many brackets I need to close before I put to the -1 power tacked onto the end here. So let's you guys help me out so that I don't get the algebra all screwed up, right? So when I divide the left-hand side by VN, That fits pretty easy. Now I'm I have 1 over Rn times the reciprocal of this thing. So if I just multiply by, I think I close it and put to the -1, I believe that's correct. So this is a horrifyingly ugly one. And it's because we're including the effects of channel length modulation, which I'm almost positive I didn't do back in 335 and 336 so that we can avoid this. So if I'm feeling squirrely, I might make you guys derive it or something without channel length modulation. It's just practice. Yeah. All right. So horrifyingly ugly thing, but we now have our 3 basic single stage amplifier types taken care of with channel length modulation effects included. If I wanted to be ludicrously brutal about this, technically speaking for this one, notice that our source isn't at ground, so we probably should have included body effects too, but I'm not going to do that because it's going to be even worse. All right, so we're gonna let that one go. Okay. So the next thing that I would like to talk about is an introduction to current mirrors. So let's look at this circuit. Where we have some source voltage VDD connected to an independent current source supplying some current IREF. I'm going to call the transistor on the left M1, transistor on the right M2. So let's call this current flowing through the drain of transistor 1 ID1, and this current flowing through the drain of transistor M2 ID2. And these 3 dots up here on the right-hand corner just represent that this is connected to some other external network. And we're going to talk about that in a minute, but we are approaching current mirrors. While we're absolutely going to talk about their nominal utility of replicating currents and all that kind of stuff, we're going to be approaching current mirrors a little bit differently in this class than we did back in our analog and electronics classes. We're going to be treating this as a sort of biasing circuit, or effectively, we're going to say, how do we make this thing behave like a current source for other stuff, right? And I know that for now, I'm approaching this in a magic space where we actually have current sources available. Okay, and we'll fix that in a little bit, all right? So this is my drain, and I guess I should technically call it drain 1, source 1. This is my gate, source 2, and drain 2. So if we wanted to analyze this guy, we're going to do it in a much more simplified fashion than we did previously. By inspection, we can see that our drain current ID1 is exactly equal to IREF. Okay. So before we move on from that, does everybody understand why I can say that? We're not dealing with BJTs, so none of our reference current is going to branch off and flow through our gates, assuming that this is, we're looking at this as a DC circuit anyway. Okay. So I can say that my gate source voltage for transistor 1 will be VTH plus the square root of twice reference divided by mu n Cox W over L1, right? So effectively, we have a feedback situation here where since we're forcing a specific amount of current to flow through the transistor, it makes the gate source voltage of the transistor be whatever it needs to be in order for that much current to flow through the transistor, okay? I can also say, go away, that VGS1 is the exact same thing as VGS2, right? Because both of my sources are at ground and my gate nodes for each of the two transistor devices are tied together. So VGS1 and VGS2 absolutely have to be the exact same thing. Since VGS2 is the same as VDS1, nominally, ID2 must be equal to ID1, must be equal to IREF. So that's why this guy is called a current mirror, right? Our reference current is mirrored by all of the transistors connected out to the right, okay? So there are a couple of important things that we need to talk about to really understand what's going on here and how we can make this guy behave like a current source. The first of what I have labeled as important notes is that M1 is always in saturation. Can anybody explain why? Okay. What do you mean by self-biasing? Like, I agree from what we talked about back in 335 and 336, but what does that really mean here? So we can see by inspection that VDS1, the drain source voltage for transistor M1, has to be exactly the same as VGS1, right? Because the drain of transistor M1 and the gate of transistor M1 are tied together. So VDS1 is equal to VGS1. Well, VGS1 will always greater than VGS1 minus VTH. So this is why this guy is always, always, always in saturation. Transistor M2 is assumed to be in saturation, which means our drain voltage VD2, what the heck just happened there, needs to be greater than or equal to VGS2 minus VTH. Important note number 3 is that channel length modulation affects so what I mean by that is that ID2 will be approximately equal to IREF plus some change in current delta I, where if VD2 is exactly equal to VGS2, delta I is 0. If VD2 is greater than VGS2, delta I will be positive. And if VD2 is less than VGS2, delta I will be negative. So to help you guys understand what I am trying to impart upon you, I'm going to draw a graph here. And I'm going to intentionally exaggerate our transistor drain current. All right. So, oops. Start off in the triode region. It's going to be fairly linear. Then it's going to curve. And because of channel length modulation, it will still continue to linearly increase like so. So let's call this point VGS1, and its representation on our y-axis will be exactly I reference. Okay. So this is a current effectively that transistor M1 is carrying for sure. Now, let's say that transistor M2 operated here. So it has a VDS value that is larger than VGS1. Still going to mirror the current, but it's going to have that little bit of error included as well because of that small signal drain source resistance. Similarly, if we chose a place where our drain source voltage were slightly smaller than VGS1, we would see that we have IREF minus delta I, okay? So it's going to be somewhere in the ballpark of mirroring it, but if we allow that voltage VDS2 to not be exactly equal to VGS2 and therefore VGS1, we do see that there's a little bit of mismatch between the mirrored current and the current that it's copying. Okay. No, it's absolutely dependent on how far away our voltage VDS is. Okay, so this is a channel length modulation bit, right? So we are assuming our VGS1 is going to be operating at some fixed value, right? So let me explain what's going on here in our original circuit. Maybe I can try to explain what's happening a little bit better. All right. Our reference current is being supplied by an independent source, right? So that means that it is just forcing that much current to flow through whatever it's connected to, okay? So that means that transistor M1 has to have that current I reference flowing through it. Okay. We know that none of that current can branch off and flow into the gate terminal of either transistor M1 or M2. Okay. So because M1 has a current of Iref flowing through it, a voltage of VGS1 must drop over it, right? Where VGS1 is given by this. So that's VTH plus what's effectively VD sat, right? Or the overdrive voltage. So transistor M1 is going to be operating in saturation, but it's more in saturation than it needs to be because we have some overdrive voltage there, right? Okay. So that's why I can say on this curve, my red curve for what transistor M1 is doing, VGS1 occurs somewhere in that channel length modulation regime, right? So where it's not perfectly flat, it's tilted up slightly because we have that pinch off point is being moved, or is effectively shortening the channel length, okay? Well, if we allow the voltage here at the drain of transistor 2 to be larger than VGS1, that means transistor 2 is experiencing the effects of channel length modulation more, right? Because it has a larger overdrive voltage. And so that's why it's out over here to the right on the x-axis and why we see more current being drawn through transistor M2. Similarly, we could lower that drain voltage VD2 below VGS1 and still keep our transistor in saturation, but we wouldn't see that it gets affected by channel length modulation because we're not lengthening the channel. So its operating point on this curve is fully dependent on how much overdrive voltage is applied. Does that make sense?
Yeah.
Okay. So we now have a fairly basic understanding of how these guys operate. So let's talk about a couple of ways in which they can be used. So the most obvious way is that we can make copies of the reference current. So we can achieve that by simply chaining multiple transistors. So here is M1 carrying a current of ID1 . Here's M2 carrying a current of ID2. This is our basic configuration. Right. But I could do this correctly. Make another copy. ID3 in transistor M3, like so. Keep on making effectively an infinite number of copies as long as my power supply is able to supply enough power to make that happen, right? So it doesn't matter how many of these replicas I make, I can still copy this current over and over and over again. Where the assumption here is that ID1 is equal to ID2 is equal to ID3 is equal if the aspect ratio W over L1 is equal to W over L2 is equal to W over L3. 3, and so forth. Again, for them to be exact copies, they would all have to have the exact same VDS voltage, right? But nominally, I can make an infinite number of copies here of something pretty close to I reference with this, right? That's fairly boring and straightforward. Another interesting thing that we can do is change the aspect ratios to let us scale copies. So if we have our basic circuit again, let's call this guy here M1 and this guy here M2. If this guy has an aspect ratio of M times W over L. Oh, and I need to connect this guy, right? And my drain current here, ID1, will be 1 over M multiplied by my reference current, right? So if I make the area larger, I'm really just making the width larger, I can effectively treat it as multiple transistors connected in parallel, right? So whenever I increase the width of a transistor, I can treat it as if it's multiple transistors in parallel. I think we talked about that probably close to 3 weeks ago at this point, right? Each one of those transistors will be carrying a portion of that current IREF. And so that's why we get this guy right here. Now, if I have N times W over L here on my mirrored side, then what I find is that my drain current ID2 is going to be N divided by M times I reference. And so I can get any scaling factor I want by properly choosing how I set my aspect ratios of these guys, right? So I can get 3/5 or 17/45 or whatever the hell I want to do just by breaking these guys down and all that kind of good stuff, right? So this is the basic operation and all that kind of jazz. We talked about this in analog electronics, probably spent the better part of a week or a week and a half on it. We covered it today in 45 minutes. Not even that actually, because we spent the first half hour talking about something entirely different. Now let's talk about something more appropriate for this class, all right? Biasing external circuitry with current mirrors. So to briefly recap, we have our current mirror, circuit, here's transistor M1. Oops. All right. Here's M1. Here's M2. Here's W over L1. Here's W over L2. We know that this voltage VGS is VTH plus root 2 IREF, or I didn't label IREF links, so I'll do that now, divided by mu n Cox W over L1 specifically. And we know that this drain current ID2 is going to be 1/2 ELEN Cox W over L2 times VGS1 minus VTH quantity squared, which will equal IREF if VDS2 is greater than or equal to VGS1 minus VTH and, W over L2 is equal W over L1. So let me ask you guys a question, because this is going to be an important figure of merit that we're going to be dealing with when we talk about how we're going to use these guys as biasing mechanisms. What's the minimum value that our voltage VD2 can have, right? So this is the voltage that I'm talking about. VD2 here, or the voltage at the drain with respect to ground. So let's treat it as if it were a nodal voltage, not necessarily VDS in this case, although it is. But what's the minimum voltage that this VD2 can have? This guy has to stay in saturation, right? That's our constraint. Exactly right, Taylor. VGS1 minus VTH, okay? So if this transistor is in saturation and we connected something else to it, what it sees is effectively this. That current IREF, it's being forced to flow through it. And the small signal resistance. Right? So it sees a practical current source, right? We have some reference current in parallel with some small signal resistance. So this current mirror is behaving as a current source for the remainder of the circuit. To make current mirror behave like an ideal current source, we need to what? So what's the difference between an ideal current source and a practical current source? Because right now we have a practical current source and we want it to be ideal. So what's the difference? All of you have had circuits one, so all of you should know the answer to this question.
I don't know what it sounds like.
Exactly right. So the practical current source has some internal resistance, R out 2 in this case. And the ideal current source, well, it has one as well. What's the internal resistance of the ideal current source? Infinity, right? If it were 0, there'd be a short circuit across it, not an open circuit across it, right? So if we want this guy to behave more like an ideal current source, we need to make R out 2 appear larger. All right. So we're going to spend the rest of this class period and probably all of Wednesday's class period talking about different schemes to do this. All right. Option number 1. All right. So we know that R out is equal to 1 divided by gamma multiplied by ID. So what we could do is make gamma smaller, right? Because the smaller gamma is, the larger R out will be. So my question to you guys is, how do we make gamma smaller? Or not gamma, uppercase lambda, my apologies.
Shorten the channel.
Other way around, we got to make it bigger, right? Recall, lambda here represents the relative change in length, right? When we are causing pinch off to occur. So it effectively makes the channel, when pinch off occurs, it effectively makes the channel shorter, right? For a very short channel device, it doesn't take a whole heck of a lot of excessive overdrive voltage to move that pinch off location by a significant amount. But if we make the channel longer, it does take a very, very large value of VDS to cause that channel length to shorten, right? So if we make our channel longer, we decrease lambda. Make L longer, decreases. Yeah. All right. So this works, but it has diminishing returns, right? There's an absolute trade-off that's going to happen, right? We're making our transistor larger, right? Because if L is longer, W has to increase as well to keep that aspect ratio the same, right? Which means we are using up significantly more space on our chip to make this resistance seem bigger, okay? So it 100% works. And generally speaking, probably the worst option that we could utilize. All right. Option number 2. What if took a transistor, let's call this guy M2. And I included some source resistance, like so. So let's call this source to generation, right? That's what it's called when we tack a resistor onto the source. What effects will this have on the small signal resistance. Well, let's look at our small signal model and find out. So let's say that this is our gate terminal. So everything, we would still have transistor M1 and all that kind of stuff connected, but all it's doing is establishing the DC bias operating point of this transistor M2. So our gate voltage here would be 0 because we had a DC voltage. Now we're looking at it from the small signal perspective, right? So our gate voltage is going to behave as if it were 0 because we're only looking at our small signal model. Here's VGS. Obviously now, between our source and drain, we have some resistance RS. I'm going to call this VGS2 just for the sake of argument. Then we're going to have GM2, VGS2, here we're going to have R out 2. And I want to figure out what this output resistance, capital R output resistance is. Looking at how can I do it? Any of you guys remember? So I'll give you a hint. We're looking in, and the network that we have contains a dependent source, but no independent sources. So go back to your circuits 1. What did we do? So superposition requires us to have multiple sources, and we currently have 0. Test source method, right? We just want the Thevenin resistance to this dumb thing. So let's apply the test source. Let's call it V-test. We measure this current I test, and our output resistance R out will simply be the ratio of V test over I test, right? Good old Ohm's law. So, a couple of things that we can observe here. The first of which is that the voltage drop across resistor RS is VGS with this polarity, right? So the source is at the minus sign, and because our gate terminal is at ground, then anywhere else we see ground is also the positive polarity terminal for that. We know that our current I test is going to split up, and some of it's going to flow through our resistor R out 2. The rest of it is going to flow through our dependent current source, GM VGS2, but then it's going to recombine. So the current that flows through our resistor RS is just I test, right? So it absolutely splits up, but then it recombines because what other path could it take to complete its loop? Good? Okay. So from this, we can say that VGS is negative I test times that resistance RS, right? The negative sign comes from the fact that the current is flowing into the negative polarity terminal, just like good old circuits 1. So if we Taylor, you look confused. It doesn't. So let me use my hands to make it dumb. All right, so we have I test flowing into this node. It's going to split. Some of it's going to flow to the left, some of it's going to flow down. And then it's going to recombine at this node. So how could so what I'm saying, I test is the current through this resistor plus the current being supplied by this current source. Those currents have to recombine here.
Right.
So I test is still this current plus the resistor current. All of that current I test, which is this guy plus this guy, so it's Kirchhoff's current law here, has to equal Kirchhoff's current law here. All of this current I test flows through this resistor RS. Okay. So if we apply KCL at our drain node, or the source node actually, we could see that I test is equal to V test plus VGS divided by RS plus GM VGS. And substituting in my Ohm's law relationship, this gives me V test over, sorry, did I make a mistake here? Yeah, I absolutely did. I'm sorry. This should be over R out. Apologies. V test over R out minus I test RS over R out minus I test GM RS. And you're being fickle. There we go. This lets us say that I test times 1 plus RS multiplied by GM plus 1 over R out is equal to V test divided by, I'll give you guys a minute to write this down because I know when I go to the next page, you're not going to be able to see it. We good? All right. So I can rearrange and say R out, again, simply V test divided by I test equal to R out plus 1 plus GM R out times RS, or R out plus RS plus GM R out RS, which will be approximately GM RS times R out. Actually, I apologize. These GMs and R outs, all of them should have 2s because we're dealing with transistor M2. I apologize for forgetting them. So what change occurred by including this resistor? So we did have an output impedance of R out 2. We now have an impedance of that multiplied by GM2 multiplied by RS. So we effectively just have a simple scaled version where ostensibly, if we make that source resistor larger and larger and larger, our output impedance, the impedance of our current source, also gets larger and larger and larger, right? So on a small signal level, this is pretty legit. But if we look at it from a DC perspective, all right, so let's draw the whole thing here. All right, so here's our transistor M1, here's our transistor M2. We know that looking in through here, we have R out is approximately equal to GM2 RS and R out 2. So the problem that we are going to have, I'll draw these in red, right? I have to include this resistor connected to the source of transistor M1 as well, right? This thing has to be perfectly matched on the left-hand side to the right-hand side so that the current is mirrored correctly. Well, that resistor will experience a voltage drop across it, right? That will be exactly equal to IREF multiplied by RS. And if our current mirror is doing its job, this resistor over here will also see a resistance of IREF times RS. So if this is voltage VGS1 and this is voltage VGS2, the voltage present at our gate with respect to ground is going to be VGS1 plus I reference times RS. So let me ask you guys now, what's the minimum value of the voltage that can occur at the drain of transistor M2 to keep this guy in saturation? Exactly right. VGS1 minus VTH plus IREF multiplied by RS. So what we find is that the increase in output, small signal output resistance constrains our drain voltage, right? So effectively, we have to make sure that that voltage drop is even higher than it was previously to compensate for this, okay? So if we're assuming that VDD is the highest voltage that we have in our circuit, what that means is that we've increased our output resistance by decreasing what we call headroom, which is the size of signals that we can apply to things, okay? So in some instances where we're amplifying maybe very, very small signals, it doesn't matter too much. But if we're trying to amplify larger signals, this completely breaks everything, right? So what we're going to talk about, I have 2 minutes left. So what we're going to talk about on Wednesday is ways to replicate this. So getting that same kind of output resistance increase by attaching stuff to the source but figuring out how we can minimize the effects of the trade-off and losing headroom. All right. See you guys on Wednesday.